Good morning, dear students, and welcome to Vista's Learning and online educational platform. My name is Denzil, your physics tutor for class 11. Let's get started with today's session. Today, we discuss an important concept, not just forces. We discuss an important concept which is called friction. So this is a session 6 of the chapter Laws of Motion. So to begin with friction, we need to understand some of the fundamental forces in nature and the various types of forces. We can classify forces under two types like we have discussed in the first session, where the forces can be classified as a contact force and a non-contact force. Under non-contact forces, you have all four fundamental forces of nature. What are the four fundamental forces that we know? Is gravitational force, and you have electric force. Now, electric force, here's a quick GIF. I hope it's a GIF. No, it's not a GIF. But here's a quick picture of how an electric force can actually be observed. So this is an experiment, an activity where you take a comb and you brush it against your hair. And when you bring those dry hair, okay, not wet hair, but dry hair. So when you brush it against your hair and you try to bring it close to these bits of paper, what you observe is those bits of paper get attracted to the comb. You must have also tried the same activity, except in place of comb, you must have used a scale. So you use a scale and you rub it against your hair, dry hair, and then you bring it close to bits of paper and you observe that these bits of paper get attracted to the scale. An explanation of why this happens is based on an electric force, namely electrostatic force, because their charges, once the charges are settled on the comb, they are at rest. So this explanation has been provided in the session 1. So you can visit at www.we-learning.in. So under the playlist, you see in the session 1 of laws of motion, there we discuss 4 fundamental forces and also how electric forces are responsible for this attraction as well as repulsion. Now, moving on to the third force, which is magnetic force. You must be quite aware of magnets. So when you play with magnets, you see that the two magnets attract each other or they repel each other depending on how you face the magnet. So magnets have usually the tendency to attract magnetic materials such as metals. So here you see a magnet that is attracting a whole bunch of pins or paper clips, which are also made up of metals. Now there are other fundamental forces which is not described. First we have a unification of electric and magnetic forces, which you'll soon be learning in your second PUC or in your 12th standard. So there you will learn the unification of electric and magnetic forces as electromagnetic force. And also there's the other fundamental forces such as a strong force and a weak force, where the strong force is observed in case of an atom. When you consider in case of the nucleons, the force of attraction between the two nucleons such as the protons and the neutrons. So the forces that are responsible for those are the strong forces or strong nuclear forces. Also you have weak nuclear forces. Well, for an example are van der Waals force, where in case of your pencil lead, when you have to write in a pencil, what you observe is that the graphite, the layer of graphite gets imparted on the piece of paper. So as you keep writing, what is happening is the layer of graphite keeps getting imparted on that piece of paper. So the force of attraction between one graphite layer and the other graphite layer are what are called as a weak force. So that is just an example of a weak force. So our understanding, our objective for today is to understand more about this contact forces. Contact forces exist only if there's an external force acting on an object. An external force which is in contact with an object and that pushes the object or pulls the object, either way. So here's a quick example of a contact forces with all the surrounding objects to this particular man who seems to be looking at that piece of paper. But what I want you to observe are the objects that are lying around. So you have a glass, you have a book, you have the chair and the books here. Now, as you observe this book, it seems to be really heavy. Or it's big, at least we can see that it is big, and especially when it comes to big books, they're very heavy. How is the table even, handling the weight of that big book? Now, if you place any object on the table, how is that object able to stay on the table? Unless the table is acting certain force on the object itself. To give you an example, first, this book has a certain weight, we say mass times gravity, has a certain weight acting on the table. Though there's a weight is nothing but a force, though there's a force that is acting on the table does not break yet. Isn't it? The table does not break yet. Why? Is because this table, by Newton's third law, it says for every action there's an opposite reaction. So the opposite reaction is a force that acts upwards. See? This force is what is called as a normal. So remember from now on that any object when placed on the table, that object has certain weight. So weight is nothing but a force. So there's a force acting on a given object like a table. Table does not break yet. That is because the table provides an opposing force called the normal force. Weight, normal, and this normal force is always perpendicular to the surface of the table. All right, now let's take another example of this ball here which is lying around. When I take this ball and try to push, okay, I'll provide some force, push. You see that the ball eventually comes to a stop. Now, why did that ball stop? Why didn't the ball just keep rolling? You might argue and say it is because of animation. Well, you can try it practical as well. Take a ball and try to roll it on the floor. Observe what happens to that ball. That ball will come to rest. Why does the ball stop after some time? This is because of frictional force that it acts on an object. Frictional force are those opposing forces on an object. Force of friction, which opposes the motion of the object, and that is why objects come to a halt. Let's take another example of this man staring at this piece of paper. So this blue color, the rectangular shaped, is nothing but a piece of paper. This piece of paper, when dropped in a glass of water, will the piece of paper float or sink? Well, go ahead, try this activity by yourself. Take a small piece of paper and put it in a glass of water. See if it floats or sinks. But you observe that the given piece of paper will float. It will not sink. So we have a piece of paper that floats. Why is a piece of paper floating on water? Is there any type of force that is pushing it upward? Yes. There's a force that pushes this piece of paper upward. This force is what is called as buoyancy, which you might have learned in your lower standards. So these make up all the common forces in mechanics, which some of them are contact forces. Mostly everything here is contact force. Here you have contact forces. Contact forces for friction. Only when the ball is in contact with the surface, you have frictional force that is observed. You also have a contact force which is a normal force only when the object is placed on the table, and a contact force which is called a buoyancy as well. The same is the case when it comes to a spring. Now some of your pens have this mechanism where a spring mechanism, you can click the pen, right? The click pen deals with the spring mechanism. Spring is also used in your laptop keyboards. When you type in your laptop keyboard, you observe there's a spring that pushes back those keys. So let us observe one of those keys. I'll try to erase this part here. So here you notice this spring, as the keys are being pushed, the spring gets compressed and then it pushes back the key upward. So this is also an example of a contact force, where the force in this particular case can be defined as negative K times X, where K is called the spring constant. K is called the spring constant. X is the displacement of that spring. How much it has been compressed or how much it has been stretched. So which can be used here. See, you can identify what is the amount that it has been compressed. So X. So using this set of information, our focus will be just on one type of contact force, which is frictional forces. So let us start with frictional force by this set of example for a block which is stationary at rest. When you apply a force on this block, now any small forces that is applied when there is no friction present, any amount of small force that is applied, the object will move with a slow acceleration, where we can define the amount of acceleration will be force by the mass. But then that is not what you observe. When you apply small forces on object, they do not move. They remain stationary. So here's an example of a force that is applied on a box, but the box does not move. And why doesn't the box move? Because of an opposing force which is called static force or static friction. So how do we define static friction? Static friction opposes the impending motion. So what is an impending motion? Motion when there is no friction present. So even by applying small force, the object will move in absence of friction. But if the friction is present, like a static friction, then the object will remain stationary for those small forces. So now let us define using by an expression. Static friction are usually denoted by F suffix S, just like this, you see. Okay, F suffix S. The maximum static friction is equals to mu times N, where mu, this is a Greek letter called mu. This mu is what is called coefficient of static friction. N, as we know, is called normal, where normal is defined as m times g. So you have static friction for maximum static friction, which is equals to mu times N. So when forces are applied less than this or equals to this, then the object will not move. That is, when the force is less than or equals to this, then the object will remain at rest. Now let's suppose we consider another case where you have applied large amount of force, the object has overcome static friction, and now it is moving. It is being displaced. When the object is being displaced, the object will eventually come to rest. Is because of this opposing friction which is acting. So friction that acts for a moving object is what is called as a sliding friction. Again, static friction, friction that acts on an object at rest, friction that acts on an object in motion. So for a sliding friction, we observe that the equation can be written in such format where Fk represents the sliding friction, the force of the sliding friction, which is equals to mu k. To show this is the coefficient of sliding friction. Here it is the coefficient of static friction, coefficient of sliding friction times the normal. Now that we have this expression, let us try to identify what will be the acceleration for this particular object when there is a friction present. So we have a sliding friction that is present for an object that is in motion. So what will be its acceleration? Acceleration, which will be equals to total amount of force applied by the object F minus the static friction that is acting, sliding friction that is acting on the object divided by mass of the object. This is how you can identify the acceleration of that box. Now let us play along with some of the parameters. Force F, if it is not continuous and once the object moves in a constant velocity, okay, if for a constant velocity, let's make note of that, for constant velocity, obviously there will be no acceleration, but what we observe is that F will be equals to Fk. This is a condition for a constant velocity where the force is equals to Fk. And by substituting in place of Fk, you get Fk minus Fk is 0, where the acceleration is 0, which is true for an object moving at a constant velocity. Another case is that if the force is not continuous, if the force is 0, when force is equals to 0, what you get is this acceleration, which is equals to minus Fk by m. So you see that the object is no longer increasing its velocity but decreasing its velocity. which means the object is trying to slow down. So it is slowing down because of this frictional force, and there's no constant force, external force acting. F equals to 0. So what you observe is that minus Fk by m is responsible for object to slow down and bring it to rest. Okay. So let's make a quick note of friction. By definition, friction is the component of the contact force parallel to the surface in contact. Frictional force, as we observed, is always acting parallel to the surface of contact. Let's go back and have a look at it. You see, frictional force is acting along this a horizontal direction which is parallel to the surface which it is in contact with. Is it true for all types of surface, even for surface that is inclined? Let's take a look at it. Here we have an inclined surface, we have an object, a box. Now if the box is moving downwards, we have sliding friction. That sliding friction will be again which is parallel to the surface which it is in contact with. So since they are two parallel, we have this definition where it says parallel to the surface in contact which opposes the impending or actual relative motion. I hope you remember what is impending. Impending meaning motion without absence of in absence of friction. Motion in absence of friction is what is called impending motion. So here this friction opposes the impending or actual relative motion. So let us try to understand this particular definition. Actual relative motion between the two surfaces. So what does it mean? Note that it is not the motion but the relative motion. Even here it says that the relative motion that the frictional force opposes. So let's have a look at this, what relative motion actually means. Let's take an example of this train, and inside the train compartment you have a box, a cargo. All right. Now practically what you observe from a point of view that is inside the train, as the train starts, from a point of view inside the train, as this train journeys, that box will remain at rest. So if you're standing inside train, once the train start moving, that box will remain as it is. But for a person, observer who is from outside, you will see the box moving with the train. Okay, I hope you remember this is what we call as a frame of reference. It depends on with respect to which observer. For an observer inside the train, the box remains rest. For an observer who is outside the train, the box is in motion. Now, this is what we observe as a practical or real life. Whereas, we do not observe something like this. Have a look at this. So the box which remains stationary due to inertia, okay, inertia where the object has the ability to stay in the state of rest or motion, due to inertia this object will remain at rest. But then that does not take place. The object also moves with the train. So why isn't it like this? Why doesn't it happen like this? This is because of the static friction. When the box is placed inside the train, due to static friction, that box moves along with the train. If static friction is absent, If there is no static friction, then you will observe something like this. Now you understand why static friction is important. So this concept is what is actually a relative motion of friction. So here you see relative motion, actual relative motion between two surfaces, one with respect to the other surface. So I hope this is clear. Now we try to solve a problem for better understanding. Let's read the question. Question says, determine the maximum acceleration of the train in which a box is lying on its floor will remain stationary given that the coefficient of static friction between the box and the train's floor is 0.15. So you've been given coefficient of static friction, and what you need to identify is the maximum acceleration. So let's make note of it. Maximum acceleration for a given static friction, which is less than or equals to coefficient of static friction times the normal. This is mu s n. Force of static friction is mass time acceleration. This is maximum. Less than equals to mu s. Normal. Normal is defined as product of mass times gravity. Since we have mass on both the sides, we can cancel that mass, and what you obtain is A, which is less than equals to mu s g. If g is taken, if g is 10 meter per second square, how much will be the acceleration? A simple calculation where you write A, which is equals to coefficient of static friction is 0.15 times 10. So you get A, which is equals to 1.5 meter per second square. So this will be the maximum acceleration of the train in which the box is lying on the floor. Beyond which, what will happen? If you go beyond if the train goes beyond 1.5 meter per second square, then the box will start moving. So the box will be set into motion in a backward direction. Okay. So 1.5 meter per second square is the maximum acceleration at which the train can travel, beyond which the box will start moving backwards. So that is all I have for today. Do visit us at www.we-learning.in to get more details about the classes, and you can also refer to some of the bridge courses where I've conducted for a session related to limits and also differential calculus. We will be soon using those concepts of limits and calculus in our next class. So until then, everyone, take care and have a nice day. Bye bye.